then I think we can start with our second talk. So I'm happy to introduce Rainer Picard from Dresden, who will give a talk on abstract Friedrichs systems and their use in complex media.
Well, thank you very much, Christian, for the introduction, and I'm very pleased to be here, if only virtually. I want to present here some work in progress that we're currently chugging away at with Sascha Trostorff and Markus Warwick. And it's one of those related topics because there will be hardly any semigroups occurring in here. I want to consider these types of equations. So the T0 is my notation for the time derivative. Then there is some extra term here, which I usually like to refer to as material law and an operator A. Here M is a bounded analytic linear operator valued function in a ball around a real point R on the real positive axis with radius R. So it's a ball sitting on the real line and touching the origin from the right. And the setup is such that the time derivative commutes with A and this material law term M of D0 inverse. That is a standard configuration in a tensor product structure sense. So we have a time factor and a space factor, and the A is sort of summarizing the spatial derivatives, and D0 is the time derivative. So, of course, to make sense of putting in an operator into a function, an analytic function, we need to have a functional calculus. And the setup here is to start with an exponentially weighted space, L2 type space on the whole real line with values in a real Hilbert space H. Associated inner products and norms are denoted like this. The inner product, by the way, is this here. So we're multiplying pointwise in H, the two factors, and then here is the exponential weight squared to integrate the whole thing. That's the underlying space structure, which allows us to get a function calculus for D0. Of course, D0 now is nothing but the usual derivative with respect to R, here through the real line. Timeline is all of R, so it's not starting at 0, but it's on the whole real line. And D0 is just the closure of this obvious derivative operator here. So in this setup, it turns out that the time differentiation is a normal operator in this space. And normal operators can be split into symmetric and skew-symmetric parts, which I've spelled out here. Actually, the bar can be dropped here and in this sum notation, even in this location. But leaving that aside, we have a symmetric part and a skew-symmetric part. And if we analyze this a little bit more closely, then the symmetric part, which is always self-adjoint in a normal case, is just multiplication by, it's just multiplication by rho, and rho was just the exponent parameter in the exponential weight. And then there is the skew-symmetric part, which is then just the rest of it. And here we want to focus on the choice rho is in positive, because that will be taking care of the issue of causality. We want forward causality, and forward causality is associated with positive rho, and negative rho would be associated with backward causality. So, yeah, now the connection to the Friedrichs systems. Friedrichs introduced some systems in the 50s, which are composed of actually an M-accretive extension of a symmetric operator, which would be the script A, and a positive definite symmetric part, which I've noted here by E0. And of course, we can take the operator we started out with and split it into these two parts by taking the symmetric part of this coefficient, and then we have A, oops, sorry about this. Then we have A as the skew symmetric part of this first term with the material law and some operator A. Now, and the choice is that the A is supposed to be coming from a skew symmetric operator, which is clear for this part because we're taking the skew symmetric part. But this A here is supposed to be stemming from a skew symmetric operator, A circ. That's my notation to indicate that in applications, we would be dealing with boundary zero conditions here. So that's the little circ on top indicating. But in abstract terms, I just have a skew symmetric operator A, and A is supposed to be an M-accretive extension of the skew symmetric operator A circ. And we can even reduce this E0 here to be 1 by pulling out square root of E0 in front and behind. You see, we have this here now is congruent to this operator, 1 plus this, and this operator inherits the desired M-accretivity from script A, and vice versa. If that is maximal accretive, then so is the A here. So in essence, we are interested in operators of this simple form. I've just summarized that in a definition here. What I would call an abstract Friedrichs system, an operator equation with an operator O congruent to 1 plus A, where A is M-accretive, an M-accretive extension of a skew symmetric operator A circ. So exactly what the Friedrichs construction does now in abstract terms. As it turns out, when you look into the literature, there is an equivalent concept, which on the first sight looks a bit more complicated, but it actually is equivalent to what I've written here, which goes back to a paper by Ern, Guermont, Kaplan in 2007. But I'll stick with this concept here. So now there's a little twist here. If you recall, the classical Friedrichs system setup is always time independent. There's no time involved. So we're suggesting to take this type of operator equation. I put an extra closure bar here because that's what's needed to get a proper solution theory, to call this an abstract dynamic Friedrichs system. This is a proper way for implementing forward causal time evolution problems. But as I just indicated a minute ago, this here is actually an abstract Friedrichs system, but in space-time, which is something that is beyond the original idea by Friedrichs. And that's the kind of problem we want to address. And just to recall a little bit of the structural theory here, well-posedness of this type of problem can be based on two separate issues. You can separate this material law part and the A in the following way. The assumption is that this material law term, D0M, D0 inverse, is uniformly M-accretive, and A is M-accretive. And then by construction, we have this commutativity, which we need to keep in mind. For a survey of the ideas behind all this, I recommend to you this survey paper, Well-Posedness via Monotonicity, by the three of us here from 2015. So we want to implement, thinking of A circ as something that has all vanishing boundary conditions possible implemented, we want to consider now, starting with this, extensions and to, for example, skew self-adjoint or M-accretive type operators. And in order to have something to extend, I'll just assume it is not skew self-adjoint, this A circ, because then there's no room left to extend. Now we take operator A as the negative adjoint of this small operator, and then we find a strict inclusion of A circ in A. So in mind having that A circ has all the boundary conditions and A is the same as A, but it has no boundary conditions involved. So following an idea by Hermann Weyl from 1940, we do an orthogonal decomposition now of the domain of A, which according to this contains the domain of A circ. And then we have take the orthocomplement. The norm of domain of A is of course the standard graph inner product of A. And so this is an orthogonal, an orthogonal decomposition in this spirit. So anything that has not everything zero on the boundary sits in this kernel of 1 minus A squared. And so this kernel of 1 minus A squared will serve for us as an abstract boundary data space. So here's this boundary data space, which now can be split into the kernel of 1 minus A and 1 plus A. That's just essentially it's the binomial formula, if you will, but it turns out to be also to be an orthogonal decomposition in the graph norm of A. So if we take the canonical embedding of these kind of kernels into the domain of A, so it's the identity really, then the corresponding orthogonal projectors on these two spaces, P plus minus, can be written as the product of iota plus minus star. That is sort of the reduction of domain of A onto the kernel, and then back with the embedding of the kernel back into domain of A. So we can factorize projections in such a fashion. We'll make use of that a little bit later. Okay, now we get to the boundary condition bit. How can we approach the boundary condition? Well, we first start with the observation that A can be represented by the bilinear form xay in the inner product of H. And then we take the symmetric part of this form, and this will be referred to as the boundary form. If you spell it out, it actually is the integration by parts formula for the operator A. So this form represents the boundary term. So now we note that if one of the factors is in the beta domain, in the domain of A circ, then this term here is 0. So that means essentially that working with beta of A in all of domain of A amounts to only using values in this boundary data space kernel of 1 minus A squared. And then another step, you see this is a form with respect to the inner product of H. So it's built from the inner product of H. But due to the nice fact that the kernel of 1 minus A squared means if I apply A twice, I'm ending up with 1, you can equally write this with the inner product of H replaced by the inner product of domain of A, so by the graph inner product. So with this observation, you can show, you can show that the boundary form splits into two parts with respect to the norm in domain of A, namely in the one that goes to the positive eigenspace, if you will, of A, and into the negative part. And the minus sign stems from the A sitting here, because the A applied to the negative kernel part gives you a -1. So now how do we get the boundary conditions into play? Well, any closed subspace of S of this boundary data space will produce a boundary constraint. We would pick this as a domain. So we extend the domain of A circ by S. And this new domain then incorporates a boundary condition. So let me just be a little bit more detailed about this. You see, that's why I introduced these embeddings. So if I take the embedding of this new domain into H, and I compose the A with the inverse of this embedding, then I'm getting a new operator AS, which has this domain and maps from H to H. Nothing happened there. But being in the domain of this operator then is what we would call a boundary condition. So now the operator A, if I restrict it to the boundary data space, to the kernel of 1 minus A squared, also the image ends up in the kernel of 1 minus A squared. And so this projection here is really just the identity. This is just to ensure that this operator A dot is an operator from the boundary data space to the boundary data space. So with this concept in mind, we get the following characterization. By this construction, we get a maximal accretive extension AS if we have a mapping from the kernel of 1 minus A dot, that's sort of the positive part, P plus, into P minus, with mu absolute less or equal to 1. And then the S is actually the kernel of this combination. So this is the projector on the negative kernel, so on this thing, minus mu times the projection on this. And if we look back, this condition ensures that the positivity of this term is not completely eaten up by this term or superseded by this term. So this needs to be almost like that, but a little bit less or equal to 1. And then we still have that this boundary data form, a boundary form, is larger or equal to 0, which is what we want for the accretivity. So, and as a byproduct, the adjoint boundary condition is very naturally just the kernel of iota minus star minus mu star times u plus star, iota plus star. So it's just the order of the projections interchanged, and instead of mu, we have the mu star. So it's then, that is the condition for maximal accretivity. This is inspired, by the way, by the analogous observations that you have for port Hamiltonian systems. And it's kind of nice to see that it also works in this general setting. Okay, another little comment about why I'm writing a dot here. The A circ was skew symmetric, and I found this very curious when I first observed it. The skew symmetric A circ produces in the boundary data space an A dot, which is then the opposite, so to speak. It's self-adjoint, and it's also unitary in this kernel. So that's why I thought it would be good to have a separate notation for this operator. Okay, now we get to the part where we combine such an M-accretive operator with a suitable material law. And just to give you an idea what these things look like and how you get them, you remember I said M is analytic, bounded, operator valued in this ball that touches the origin. And of course, as you can imagine, D0 is a normal operator, so we have a spectral representation for the time derivative, and the spectral representation is actually produced by a combination of a multiplication by the exponential weight, which gets us from the weighted space into L2, and then the Fourier transform. So this is just a special Fourier Laplace transform here. And here's the adjoint. So we're taking M of 1 over I omega plus rho, if you will, but then we let the omega go and turn it into a multiplication operator. This is the notation here, M0, multiplication by the Fourier equivalent of the time derivative. And then you transform it back with the inverse Fourier Laplace transform. And that's what this function here is. That's our material law. And the positivity condition that we imposed, oops, that's supposed to be a Y. Didn't make it into the print. Okay. The strict positivity condition that we require can be written in this way. You see, that's the leading term in our abstract dynamic Friedrichs system, and that's supposed to be strictly positive, well, at least for a sufficiently large rho. That's the point. So there's a inconspicuous little rho here. That's the weight factor that we can still adjust to make this a feasible problem. Now, of special interest in many applications is the zero analytic case, where M is actually an analytic in a neighborhood of 0. And then, of course, we can fit in a little ball of that type, which just touches from the right, the origin. That's a good situation to be in. And in applications, it's frequently used. And then we end up with a special version of this general statement of earlier on. So if we have that A and A star are accretive, that is, A is M accretive, and M is zero analytic and satisfies this condition, slightly reduced compared to the earlier one, I only need to know M of 0 and M prime of 0. So it's rho times M of 0 plus M prime of 0, product with X on both sides. For X in the unit ball, then this needs to be positive. That's the requirement. And since this inner product here, there's supposed to be an H down here, so it's the underlying Hilbert space. The inner product here being symmetric induces that from of M prime of 0, we only use the symmetric part, and we also need to ensure that M of 0 is itself self-adjoint. Otherwise, we can't get these estimates here. So that's how it works. This is the crucial assumption. Then the abstract dynamic Friedrichs system, as it is written here, is well posed for all sufficiently large rho. Okay, so now for the last minute or two, I'll just want to show you the application of this in a concrete context. Look at electromagnetic waves in simple media. So here are the Maxwell equations in the usual, written in the usual block structure. Here's E and H, D and B, displacement current and magnetic induction. And what I call material law is the connection between dB and EH. And here in this particular instance, classically, that is this block diagonal matrix with epsilon and mu in the diagonal. And maybe if we have conductivity involved, then there is a second term and with a D0 inverse. So it's just a simple affine function of D0 inverse. So it fits the bill of being zero analytic function of the inverse time derivative, which is the integral, really. Okay, and the requirements are written here. Rho epsilon plus sigma and mu are supposed to be strictly positive definite for sufficiently large rho. Well, if epsilon itself is strictly positive definite, then we can always achieve that for any rho which is larger than 0. So let's have a brief look at this construction of M-accretive extensions. So first we have a circ, which has this form. So all the boundary conditions for curl are implemented, usually by taking the curl on C1 functions with compact support, and then take the closure of that. That is one of the operators, and the in the off diagonal, we have the same operator with a negative sign. Now, in this situation, we have a nice symmetry. Due to the block structure here, we have that A, if we commute it with this simple matrix, then it turns out, then it becomes the negative part. And this structural feature has a side effect, namely that this simple block matrix is actually a bijection between the different kernel spaces of the boundary data space, the two components. Okay, and this is the type of boundary condition we are thinking of now, using that earlier theorem. And the simplest choice would probably be to take mu as just this kind of a block diagonal matrix, because as we said, it maps the plus space into the minus space. So this is fits together. And if we calculate out what that means, then this is indeed just the standard electric boundary condition, that E is in the domain of curl circ, which is the same saying in classical terms that N cross E on the boundary vanishes. That's the classical standard electric boundary condition. And here, as another extreme case, if we simply take mu equals 0, we get an impedance type boundary condition. Just calculate this out, and this is the type of boundary condition we get. This one is actually dependent on this. So just this one boundary condition, which looks impedance type if you notice the correspondence between curl dot and N cross. So, and this is the last slide here, just to have a more interesting material law to combine with. We look at so-called Drude-Lorentz type models, which are material laws, which are actually rational functions. And here just products of polynomials and inverse of polynomials. That's the type of condition that Drude and Lorentz introduced for describing more complex materials. And this brings me to the end. Thank you very much for your attention.
Yeah, thank you, Rainer, for this very nice talk. Are there any questions or comments?
I have a question.
Sure.
I would like to know, when you look at this Maxwell equations, can you somehow state boundary conditions in L2 in the boundary, or is it in your abstract boundary space?
Well, there are variants of doing that, but then you have to slightly modify your curl. You can combine the curl with the boundary trace of curl as a column, and then take up here the adjoint of this column construction. And then you reduce your domain of curl to those elements which are in the domain of curl and have boundary trace in L2. And this turns out to be a closed linear operator. And you just took the adjoint, the negative adjoint up here. And so you again have this self-adjoint situation. So that's how you would handle that case, yeah.
Okay, thank you.
Mhm.
Okay, thank you. Are there further questions or comments?
I have maybe a silly question because I'm not familiar with this research. Is it possible to represent the solutions of the Maxwell equation as an explicitly given semigroup?
Yeah, that's an interesting question, because that's the the thing in the background here. If you're looking for like I just introduced, these Drude, oops, here they are, these Drude-Lorentz type models, you have lots of time derivative inverses involved, and well, the semigroup enters the picture because it is the fundamental solution of equations of the type D0 plus A. This is not the case here, so you would take a different fundamental solution would be more appropriate, right? The idea is to have a fundamental solution and then express general solutions by convolutions with it. And having complicated material laws would involve then different fundamental solutions, which are not exponential functions anymore. A point in case, just an extreme case, your material law could be just D0 inverse. And then Maxwell's equations were 1 plus this Maxwell curl minus curl thing, 1 plus A. There's no time derivative occurring at all, but it's still manageable in this framework. But of course, you don't have a semigroup, right?
So
you still
there
have
is
a fundamental solution. You still have a fundamental solution. 1 plus A G equal to Dirac delta times U0. U0 would be your virtual initial value, right? So in this form, you can solve this. That would be your fundamental solution. And then convolution with that would give you a general solution if you wanted to go that way. But it's not a semigroup.
Mm-hmm. And
Does
there
that
is no
answer?
simple explicit formula for that.
Well, in this case, the one I mentioned with the one, of course there is, but every problem is an issue in its own right. Yeah, I mean, it's like in the standard theory of partial differential equations with constant coefficients. You can't use just one fundamental solution for all problems. Every problem has its own fundamental solution. Yeah. So the semigroup appears if you assume that it is explicit in time D0 plus A. But here we have, we want to include complicated material laws, and that makes it disjoint in essence.
Thank you.
You're welcome.
Okay. Any further questions? Quick questions? Okay, this does not seem to be the case. Then let us thank Rainer again. And we